Hi, in this module, I'm going to talk about Laplace smoothing for guarding against overfitting. So let's review maximum likelihood estimation networks. Remember last time we had an example of a two-variable network, a genre of a movie and the rating of a movie, where their joint distribution is given by probability of a genre times probability of rating given. And now we don't know these parameters, but we want to estimate them from data. Suppose we gather 5 data points here. And the way that maximum likelihood estimation works is by counting and normalizing. Parameters here are probability of G. And for that, I'm going to count the number of times G shows up and normalize. And for probability of R given G, I'm going to look at the number of times each of these configurations shows up, and then I'm going to normalize each one conditioned on the value of G. So if you look at these estimates, you might notice that there's something funny going on here. So the probability that these parameters assigned to a rating of 2, given that there's a comedy, is 0. It doesn't show up in this row of this table, which means that it's 0. So do we really believe this? Just because we didn't see an example of a comedy being rated as a 2, are we licensed to just give it a probability of 0? Well, that would be very close-minded. So this is a case where maximum likelihood has overfit to. There's a very simple way to fix this called Laplace smoothing. And the idea is that we're just going to add a lambda, which is some positive value, let's say 1, to each count. So let's do a maximum likelihood with Laplace smoothing. So training data is the same as before. And what we're going to do is for each of these local distributions, we're going to preload a 1, lambda more generally, into this position. And now I'm going to go through the training and count as usual. So I add 3 and I add 2. And then I'm going to normalize over these combined counts. And same with the probability of R given G. For each of these configurations, so now I have to actually instantiate all possible configurations. I'm going to load a 1 into each of these counts. And then I'm going to look at my training data. And I'm going to add 2. There's 2 D4s, 1 D5, 1 C1, and 1 C5. Now, given these counts, I'm going to normalize to get my probability estimate. Look at all of the Ds, count them up, normalize. I get some quantities here. And look at all of the case rows where G, C. I'm going to sum and normalize. So now, what we revisit our probability estimate of R equals 2 given G equals C. This was 0 before, but now it's here. That's 1 over 7, which is greater than 0. So now, because we've smoothed these estimates, now we have a little bit more probability on even those outcomes that we've never seen during training. So the key idea behind maximum likelihood with Laplace smoothing is follows. So we're going to go through each distribution and partial assignment to the parents of a node and the node itself. And we're simply going to add lambda to the count. Now we do maximum likelihood estimation as usual. So we're going to go through the training data and increment those counts based on what we saw. And then we count and normalize, and that's it. So the interpretation that we can place on Laplace smoothing is it's like we hallucinated lambda occurrences of each local assignment. So sometimes these lambda counts are called pseudo counts because they're not based on the data, they're kind of made up or virtual counts. So you can think about pretending you saw some examples before you saw data and then doing maximum likelihood estimation. So how much should lambda be? How much smoothing should we have? And how does it interact with the data? There's 2 observations I want to make. First is that the more you smooth, which means that the bigger lambda is, the closer you're going to push the probability estimates closer to the uniform distribution. So for example, if I just smooth with lambda equals 1/2, then, and I observe only a d here, then the probabilities estimates are going to be 3/4 and 1/4. Whereas if I smooth with 1, then the probabilities are going to be 2/3 and 1/3, which is closer to 50/50. The second observation I want to make is that no matter what you set lambda to, the data wins out in the end. So suppose we only see examples of dramas. So suppose that we're smoothing with lambda equals 1, and we saw only one example of g equals 1. Then again, the probability estimates are 2/3 and 1/3. But suppose we keep on seeing dramas over and over again. So we see 998 of them. And now if we count and normalize, then we get the probability estimate as 0.999 of drama, which is much closer to seeing only dramas. So to summarize, we looked at Laplace smoothing for avoiding overfitting and estimating Bayesian networks. And the key idea is that we preload counts with a lambda, and then we're going to go to training data and we add the counts based on our data, and then we normalize. So the smoothing pulls us away from zeros to the uniform distribution, but in the end, all the smoothing gets washed out with more data. That's the end.